So in this lecture, I want to show you how to model chemical reactions with Excel. And I sort of assembled the tools. So we're going to use Excel. Then we're going to use PQCalc that you already are a little bit familiar with. And we're going to use, if we want to, AI to help us out with questions about how to do this. So on PQCalc, I already gathered everything, what the reaction is. It's exactly the same as on the worksheet. So A plus B reacts to form C plus 2D. I'm going to give you the rate law. And here's an example of using an AI to quickly get an overview what a rate law is. So the rate is dependent on the concentration of A and B with coefficient or orders of reaction in A and B that we would have to find out first, but I'm just giving it to you so we can then see how we can predict the future knowing this. So that's this. And I'll actually click return so we have this in a better format. Just two things. If you just want to show a formula in PQCalc, you put an at in front of it and then knows not to calculate. And if you want to show a formula, a chemical formula, you put a exclamation point in front of it. The rest should be known to you, the syntax, but you can refresh yourself with the tool that I gave you. So this is the reaction. So you see it's nicely formatted. And this is our rate law in the specific case. So it is first order in A, first order in B, overall second order. And just to remind you, if you want to calculate the change in A, concentration of A, you would have to take the change in time times the rate, and then with a negative sign in front of it because it's a reactants, and reactants get used up. And again, if it were C, then it would be plus the rate. And if it were D, it would be twice the rate times delta T. Okay, delta refers to change, right? So delta T is how much time progresses, and delta concentration means how much did the concentration change in that time. I'm giving you some arbitrary starting with conditions. So the concentration at time 0, that's the subscript here, is 1 molar. The concentration of B is 0.5 molar. We'll start out with a time increment of 1 second, and K is supposed to be 0.05, 1 over molar times seconds. So we talked about this. K has different units depending on what kind of reaction it is, what the overall order is of the reaction. Okay, what can we do with this? Well, for the specific case, we can apply these relationships. So if I want to know how much we predict A to change under these conditions, I can apply this after I figure out what the rate is. So let's do that first. If you have a formula like this, I think you can click on it. Yeah, and it just gives you this. But we're going to put some subscripts on there. So this is the rate at the beginning. K is K, that doesn't change, it's constant. But here, which concentration? The one at the beginning and the concentration at the beginning. So this is A sub 0, B sub 0, and then we can calculate the rate. When we do that, we can see whether our units were correct, right? Because the rate is supposed to be molar per second, how much has changed concentration divided by time. Let's see if I did this correct. So you plug these in, and then you can see one of these molars cancels, and the other one stays on the numerator, and so we get 0.025 molar per second. That's how much it changes. So it starts out at 1 molar, and then with this rate, it would go down by 0.025. Okay, that's the rate. And now if I want to know what happens after 1 second, I can use this other relationship that comes from the definition of the rate. So the rate is equal to change in concentration divided by delta t times a small number, in this case -1, because our reaction has a 1 in front of it, and it's a reactant, so that's why it's negative. Anyway, I can be nice and lazy here again and just click on here, but I have to make sure I want to know at time 0, how much does the concentration change? And for that, I need the rate at time 0 times delta t. Delta t will always be 1 second in our simulation. Okay. Let's plug this in, and not so surprising, we get that the concentration changes by minus 0.025 molar in 1 second. And you can see it's negative. That's good because it's a reactant, and we expect reactants to go away. Okay. So far, so good. With that information, we can actually calculate what the concentration is after 1 second. And we'll call that A1. And that's equal to A0. And I can be really lazy, I think, and just click on stuff too. Nope, that didn't work. Apologize. So A0 plus the change. So this is, I think, the first time that we're doing this. What I'm saying is, if I know how much concentration changes over 1 second, and I know what it was before, that's A0, then I can just add this concentration plus the change, and I get the new concentration. So we started out with 1 molar. Now it's 0.975 molar. We have to do the same thing with B, but this is going to be just a copy-paste job here. That would be more copy-paste, but it's not. Okay. So this will also be minus the rate 0, because it's also a reactant, and times delta t. Delta t here. And that's also minus 0.025 molar. Not surprising, because they're in a one-to-one relationship. So if one changes that much, the other one has to change by the same amount. Right? That's what or the same concentration in this case. That's what the coefficients tell you. Okay, and then just to finish this up, then after 1 second has passed, we would expect that B is also smaller, so we have to take this B0, and we have to add the change, and of course the change is negative, so and we also reduce the concentration of B. So both went down by this 0.025. Okay. Where we're going with this? Well, now I want to know what happens after 2 seconds. So I have to calculate the rate again. So this will be rate after 1 second. What was my rate law? It's K times the concentration of A times the concentration of B. But that concentration has changed. So after 1 second, we no longer can take A0 and B0, but we have to take A1 and B1. Because at that point, concentrations are already lower, rate goes down. So I made a mistake here. I really wanted to calculate the concentration at time point 1. So I can quickly fix that by going back. So I can copy this for later. That's what I actually wanted to do, but I used the wrong name here. So that doesn't make sense. This is going to be the concentration at B after 1 second. I get that by taking the concentration at the beginning and adding the change to it. So the result is the same. I just want to make sure that this that's the right name. And now I can calculate the rate. after 1 second. So it's 0.023 molar per second. The first rate we calculated was 0.025. So the rate is going down as the concentrations are going down. So this is typical for reactions that they slow down over time because we have less and less reactants because they react to form products. Okay, so this was a lot of calculation, right? If we wanted to know what happens after 100 seconds, guess what we have to do? We have to do this 100 times. And you already saw that I made a mistake here in step 1. So that's going to be kind of hard. So what we want to do instead is put it into a spreadsheet. Okay, and spreadsheets don't know about units. So it's good that we went through this with units first, and then we can see if we had to do any unit conversions, and we can use these values to actually troubleshoot whether we made any mistakes or not. I'm going to go forward to the start here again, and that will give us a good idea what we have to put in there. So the first column will just be time, and then the second column will be the concentration of A, and I'm not writing 0 or anything there because it's going to be for all time points in that column. It's going to be concentration of B, then we'll get the rate at this point, and then we'll get the change in A and the change in B. Excel doesn't do these Greek letters, so I'm going to just write delta for A, capital Greek delta, and then delta A. This one will be delta B. And then we want to know, that's it. So we can give ourselves a little bit more space because there we go. Nice. I can put some things in. So always we'll start at 0, and these are concentrations we have in the instructions. And here's our rate. Oh, we don't know the rate. We have to calculate this. Okay. So I'm going to stop right here because it's beeping.